In general relativity, the Bianchi identity is the mathematical rule ensuring the geometry of spacetime remains perfectly smooth. A previous theorem within the ODTOE framework established this identity by calculating it across two entirely independent mathematical paths. But that proof had a significant limitation. It was tested exclusively against a vacuum Schwarzschild background, a hypothetical universe containing absolutely no physical matter. In a completely empty space, the equations for both paths naturally cancel out to zero. The calculations never have to process any actual physical data. To see if this theorem holds up, it must be subjected to a stress test inside a non-trivial environment, one filled with the mass and energy of a real cosmos. This requires moving to the FLRW metric, a mathematical model representing a flat, expanding universe. A law of physics remains incomplete on paper until its mathematics survive the messy, chaotic reality of a physical cosmos. To test the FLRW metric, researchers split the calculation into two distinct computer-driven evaluators. Path 1 operates on pure geometry. It calculates the expanding universe by analyzing the kinematics of spacetime itself, completely ignoring any physical matter. Path 2 evaluates pure physics. It approaches the universe strictly through thermodynamic conservation laws. This second path relies on Noether reduction. The underlying logic depends entirely on the continuous conservation of mass and energy as the universe expands. Comparing these paths requires an absolute guarantee that they do not influence one another. The experiment implements an anti-circularity audit, a strict programmatic firewall. The two Python programs share no helper code, do not import each other, and cannot pull data from a shared memory cache. In complete isolation, both solve the expanding universe equations, down to a 50-digit precision limit. If both isolated pipelines output the exact same 50-digit number, the result is an undeniable physical truth, rather than a shared coding artifact. The two paths are run through four chronologically distinct eras of cosmic evolution. The first scenario tests the early, violently hot universe. This is the radiation-dominated era, occurring before the first atoms formed. As the universe expands and cools, the background shifts. The second scenario tests the matter-dominated era, where raw energy coalesces into physical structure. The third test plunges the evaluators into the lambda-dominated era, defining a late-stage universe characterized by empty space and accelerating expansion. The final scenario models our current reality, the mixed ΛCDM era, using the precise energy fractions observed by the Planck Space Observatory. Testing the identity against these four radically different stages proves it survives any changing cosmic condition. Researchers plotted a grid of 16 specific data points. They measured the four cosmic eras across four distinct moments in time, ranging from a fraction of a year to 1,000 gigayears. This table plots the final outputs from both evaluators across all 16 scenarios. At every test point, the difference remains below 10 to the negative 45th power. Notably, during the matter era, Path 1 records an exact 0, while Path 2 generates a microscopic error. These slightly different residual trails confirm the strict programmatic firewall held up. The two codes process the math entirely independently before converging. With this level of precision across all scenarios, Theorem DT1 is strictly validated, officially closing the open caveat in the mathematical framework. The pure geometry of space and physical matter calculate to the exact same outcome. They are inextricably linked, forming a single, unbroken reality.